Beyond the name itself whispers of ancient secrets. This distant world is called Varuna, named for the powerful Hindu deity who ruled the cosmic waters and the infinite night sky. In those ancient stories, Varuna was a celestial sovereign, a keeper of cosmic order who presided over the vast, dark, and fluid expanse of the universe. It is a name that evokes both profound depth and impenetrable darkness. The choice now seems less like a simple label and more like a strange, almost prophetic act of foresight. When astronomers first glimpsed this faint speck of light drifting in the Kuiper Belt, they saw a dark, icy body orbiting in the perpetual night of the outer solar system. It was a place defined by frozen volatiles, substances that would be liquid or gas closer to the sun, hinting at its own kind of primordial, locked-away ocean. They had, without fully realizing it, named a modern astronomical mystery after an ancient god whose domain it perfectly mirrored a realm of dark skies and cosmic waters. This uncanny alignment between myth and reality gives the entire investigation into Varuna an eerie resonance, as if the ancients had somehow glimpsed the nature of this frozen sentinel long before our telescopes ever could. The name was not just assigned, it was revealed, setting the stage for a world that seems determined to live up to its legendary title. That legendary name now confronts us with its first concrete and utterly baffling physical trait. Varuna spins, and it does not spin slowly like a ponderous giant, but with a frantic, dizzying speed that defies all expectation. This distant world completes a full rotation on its axis once every 6.34 hours. To put that into perspective, our own Earth takes a leisurely 24 hours for a single day and night cycle. Varuna, an object far out in the deep freeze of the solar system, accomplishes the same feat in barely over a quarter of that time. For a Kuiper Belt object of its estimated size, this is not just unusual, it is extreme. Imagine a ball of ice and rock, hundreds of miles wide, whirling through the void like a top set spinning by a giant's hand. This rapid rotation presents an immediate and profound mystery. Physics tells us that such a fast spin should generate tremendous centrifugal force, enough to literally tear a loosely bound object apart. If Varuna were a simple pile of rubble held together only by its own weak gravity, this furious pirouette should have shredded it eons ago, scattering its pieces into a wide ring of debris. The fact that it remains intact, a single coherent world, means it must possess an unexpected internal strength. What is holding Varuna together against the forces trying to pull it asunder? This question forces us to reconsider everything we assume about its composition. Perhaps it is not a fragile rubble pile at all, but contains a surprisingly solid, rocky core that provides a strong skeletal framework. Or maybe its icy mantle is not brittle, but possesses a strange, malleable strength under those unimaginable cold temperatures, acting like a thick, viscous glue. Its very survival as a rapidly spinning body suggests a hidden toughness, a structural integrity that we simply did not anticipate from a denizen of the dark, frozen fringe. The speed of its day is a glaring clue, a warning written in motion that we are looking at something far more complex than a simple, ancient snowball. This frantic spin warps the very body of Varuna, sculpting it into a shape that challenges our celestial expectations. That incredible rotational speed does not just hint at internal strength, it actively reshapes the world. The relentless centrifugal force generated by spinning so fast stretches the object at its equator and flattens it at its poles. Think of a potter throwing clay on a wheel, how the spinning mass pulls outward, transforming a sphere into a wider, flatter disk. For Varuna, the effect is likely even more extreme. Current models, based on its rotation and estimated density, suggest it is not a sphere at all. Instead, it is probably a profoundly elongated ellipsoid, shaped something like a stretched-out football, or perhaps even a flattened pancake. This is a bizarre form for a world of its size. Most large bodies in our solar system, pulled by their own strong gravity, settle into a nearly spherical shape, a state called hydrostatic equilibrium. Pluto, for instance, is a sphere. Even many mid-sized moons are round, but Varuna's gravity appears too weak to overcome the distorting power of its own spin, leaving it permanently deformed. We are looking at a world that is fundamentally lopsided, a cosmic top frozen in a state of extreme tension. Directly confirming this shape from Earth, however, is a monumental challenge. Varuna is so distant and faint that even our most powerful telescopes see it as little more than a single point of light. We cannot simply take a picture and see its football-like form. So how do we know? The answer lies in the careful study of its flicker, its light curve. As Varuna rotates, its elongated shape presents different faces to us. When we see it from the side, its long axis, we observe more reflective surface area, so it appears brighter. When it turns and we face one of its pointed ends, we see less area and it dims. By meticulously measuring these rhythmic brightenings and dimmings over its 6.34-hour rotation, astronomers can map the outline of this distant puppet shadow. The data paints a clear and consistent picture of a highly asymmetric world, its light pulsing with the signature of a shape that is anything but round. This makes Varuna a standout oddity, a principal member of the Kuiper Belt that refuses to conform to the standard roundness of planetary bodies, forever stretched by the silent, furious momentum of its own day. This distorted shape provides the first crucial clue to something even more bizarre hidden within. To understand how a world can spin so fast without flying apart, we must peer inside, and that is where the mystery deepens into strangeness. Astronomers have calculated Varuna's density, a fundamental property that reveals the nature of its interior. The results are astonishing. Current estimates suggest Varuna has an average density lower than that of liquid water. If you could find an ocean large enough, this entire distant world would theoretically float. This is a profoundly counterintuitive idea. We are not talking about a fluffy cloud or a block of styrofoam, but a celestial body hundreds of miles across. How is such a thing even possible? For a mostly icy object, a density this low points toward an interior that is not solid all the way through. One compelling explanation is that Varuna is incredibly porous. Imagine a gigantic cosmic snowball, but one that was never packed down tightly. Its structure could be a loosely bound aggregate of icy rubble and dust, with vast networks of empty spaces and gaps between the chunks, like a celestial sponge frozen in time. This porosity would lower its overall density dramatically, even if the actual materials it is made from, water, ice, and rock, are themselves denser. But there is another, even more speculative possibility whispered in scientific circles. Could some of that low density hint at larger voids within? Not just tiny gaps, but substantial empty spaces, perhaps even caverns or a honeycomb structure deep inside its icy mantle. The idea of a world with a partly hollow interior sounds like science fiction. Yet for a fragile, rapidly spinning body that has never experienced the crushing pressures of a planetary interior, it cannot be entirely ruled out. We see hints of this in some comets and smaller asteroids, which are often found to be highly porous rubble piles. Varuna may represent the largest known example of this fragile architecture, a delicate palace of ice and shadow held together by the faintest whisper of gravity. Its very existence in such a tenuous state is a puzzle. How did it form without collapsing into a denser ball? How does it survive collisions, even minor ones, in the crowded Kuiper Belt? This low density paints a portrait of a world that is not a solid planet, but a fragile relic, a ghostly assemblage from the solar system's dawn that has somehow, against all odds, kept its delicate form for billions of years. This fragile, ghostly world wears a coat of deep crimson. Varuna's surface is not the bright, reflective white of pure water ice, nor the dull gray of bare rock. Instead, it is stained one of the darkest, reddest hues observed anywhere in the Kuiper Belt. This is not a subtle tint, but a profound coloration that speaks of ancient and relentless chemical processes unfolding in the deep freeze of space. When sunlight, incredibly faint and distant, finally reaches Varuna, the surface does not reflect back a full spectrum of light. It preferentially absorbs the shorter, bluer wavelengths, leaving only the longer, redder wavelengths to bounce back toward our telescopes. The result is a distant world that glows like a dying ember against the black velvet of the outer solar system. This redness is a direct chemical fingerprint, a sign that the pristine ices on its surface have been fundamentally altered. The most likely artist behind this transformation is a relentless rain of cosmic and solar radiation. Over billions of years, high-energy particles and ultraviolet light from the sun, even at that vast distance, have been bombarding the simple ices on Varuna's surface. These ices contain familiar molecules like methane, nitrogen, and water. When radiation slams into them, it breaks their chemical bonds and forges new, far more complex ones. The result is a class of sticky, organic compounds known as tholins. Tholins are not a single substance, but a vast family of complex, carbon-rich molecules that are notoriously difficult to study because they do not form naturally on Earth. They are essentially prebiotic goo, the rudimentary building blocks for more complex chemistry, and they are almost always dark red or brown in color. We see evidence of tholins on other distant worlds, like Pluto and its moon Charon, and on Saturn's moon Titan, where they form the particles in its thick orange haze. On Varuna, this irradiated sludge would accumulate over eons, creating a thin but pervasive veneer that paints the entire world in shades of rust and blood. Yet the plot thickens because Varuna's redness is not uniform. Careful observations reveal that its color varies slightly across its surface and even over time. Some areas may be a deeper, more intense red, while others appear slightly less so. This variation is a critical clue, a message from the surface itself. It tells us that Varuna is not a static, dead world. Something is actively refreshing or altering its complexion. Perhaps fresh, bright ice is occasionally exposed from beneath the dark red layer. This could happen through geologic activity, like the slow churning of its icy crust, or through impacts. A small collision could blast away the dark tholin coating, revealing the pristine, pale ice underneath, which would then slowly redden again under the relentless radiation. The variations in color are like a historical record, with the deepest reds marking the oldest, most irradiated surfaces, and the less red areas hinting at recent events that have turned a new page in its geological story. This makes Varuna's dark red face not just a curiosity, but a dynamic chronicle written in chemistry, a billion-year diary of radiation, impact, and change on a world we once thought was frozen in time. That dark red thalline coating is more than just a stain. It is a sealant over a potentially volatile world. Beneath that irradiated crust lies the core of our next mystery, the question of whether Varuna can ever breathe. For a body so distant and cold, the very idea of an atmosphere seems laughable. At its average distance from the sun, temperatures hover barely above absolute zero, cold enough to freeze air itself into solid blocks. Any gases like nitrogen, methane, or carbon monoxide should be locked permanently as ice on the surface, as inert as stone. Yet the solar system is full of surprises, and frozen worlds sometimes wake up. The leading candidate for such a temporary awakening is the eccentricity of Varuna's own orbit. Unlike Earth's nearly circular path, Varuna's orbit is an ellipse, meaning its distance from the Sun changes significantly over its 280 Earth-year journey around it. For a portion of that long orbit, it ventures slightly closer to the Sun's feeble warmth. This periodic thaw, however slight, could be enough to trigger a remarkable transformation. Surface ices, particularly volatile ones like nitrogen or methane, might not melt into liquids, but they could sublimate, turning directly from solid into gas, just like dry ice does here on Earth. If this happens, these gases could form a very thin, temporary envelope around Varuna, a fleeting atmosphere that exists only for a cosmic season before freezing back onto the surface as it retreats in the deeper cold. This would make Varuna a chimera, a world that periodically shifts between two states, a dead, frozen ball and a world with a ghostly, tenuous breath. The search for this phantom atmosphere has been intense but frustrating. Astronomers point their most powerful instruments at Varuna not to take pictures, but to dissect its light into a spectrum, a chemical barcode. They look for the telltale absorption lines that would indicate gases like methane or nitrogen are present in a diffuse cloud around the body, filtering the sunlight it reflects. So far, the results are inconclusive. Some observations have hinted at the spectral signature of methane ice on the surface, but a confirmed gaseous envelope remains elusive. The challenge is immense. Any atmosphere would be extraordinarily thin, perhaps 1,000,000 times less dense than Earth's air, and it would exist only intermittently. Catching Varuna in an active state of outgassing is like trying to photograph a single, specific wave on a distant shore during a once-in-a-century storm. You have to be looking at exactly the right moment. This lack of evidence is itself a clue. It suggests that if Varuna does have an atmosphere, it is an exceptionally transient and fragile phenomenon, or that its surface ices are trapped beneath a thicker, less volatile layer that acts as a permanent lid, preventing any escape. The ongoing hunt continues, because finding even a whisper of gas would revolutionize our understanding of this distant world. It would mean Varuna is geologically or seasonally active, a place where change still occurs, and it would provide a direct sample of the primordial gases from the solar system's birth, preserved and occasionally exhaled from the deep freeze. For now, the question of its breath remains suspended, a held whisper in the dark. The deep crimson of its surface is a solitary signature, a lonely beacon in the dark. This solitude extends beyond mere color into the very architecture of its space. Varuna, unlike most of its large neighbors in the Kuiper Belt, appears to be profoundly alone. It has no known moons. This absence is a glaring anomaly that speaks volumes in its silence. Consider the company it keeps. Pluto has 5 moons, including the massive Charon. Haumea has 2 and a ring system. Eris has 1, Dysnomia. Even Makemake, a world quite similar in size to Varuna, is suspected to have a small satellite. Moons are not cosmic luxuries for these distant worlds. They are fundamental records. They are the ledgers of the ancient violent era when the outer solar system was a chaotic construction zone, a place where giant impacts were the primary method of planet building. When two sizable objects collided, the debris from that colossal crash would often coalesce into one or more satellites orbiting the larger survivor. The presence of moons, therefore, is a standard birthmark for large Kuiper Belt objects. It is a sign of a dynamic past, a history written in gravitational bonds. Varuna's lack of such companions is a deafening silence in that history. So why is it alone? One possibility is that Varuna's formation was strangely gentle. Perhaps it accreted slowly from the primordial disk of dust and ice without ever experiencing a giant, moon-forming impact. It simply grew, solitary and undisturbed, from the cloud of material around it. This would make it a rare fossil of a quieter process, a world built by accumulation rather than catastrophe. The other, more dramatic possibility is that Varuna did have a family once, and it lost them. Its frantic, elongated spin is a key clue here. That extreme rotation is precisely the kind of motion you would expect from a massive, off-center impact, the very type of collision that typically creates moons. So perhaps, billions of years ago, Varuna was struck a glancing blow by another large body. The impact could have been so violent that it set Varuna spinning like a top and launched a cloud of debris into orbit. But then, something went wrong. The gravitational environment of the early Kuiper Belt was a crowded and unstable place. The gentle tug of a passing giant planet, like Neptune, or the repeated gravitational nudges from other large objects could have easily destabilized any newly formed moons. Instead of settling into stable orbits, these infant satellites might have been stripped away, cast adrift to become independent small bodies, or to crash back onto Varuna's surface. Its current loneliness, then, would be a form of cosmic bereavement, the empty space where a family once was. This solitary state has real consequences for how we study it. Without a moon, astronomers lose a critical tool for unlocking Varuna's secrets. The orbital dance between a primary body and its moon is a gravitational scale. By measuring the moon's orbit, scientists can calculate the mass of the main world with incredible precision. For Varuna, we have no such partner. Its mass, and therefore its density and internal composition, must be estimated through much less certain methods, like analyzing its influence on the motion of other distant objects or studying its rotation. This leaves a frustrating margin of error in our understanding of what it is truly made of. Its missing family thus creates a double mystery, obscuring both its past and its present nature, leaving us to wonder if we are looking at a world that was born alone, or one that was tragically orphaned. This profound darkness is measured by a number called its albedo. An albedo of 1 would mean a surface reflects all light, like a perfect mirror, while an albedo of 0 is absolute black, absorbing every photon. Fresh snow on Earth has a high albedo, around 0.9. Varuna's albedo is shockingly low, estimated to be between 0.05 and 0.15. This means it reflects back only about 5 to 15% of the faint sunlight that reaches it, making it one of the darkest known objects of its size in the outer solar system. This is the central contradiction. We know from its density and spectral hints that its surface is dominated by water ice. Water ice is brilliant. It is what makes snowfields and glaciers gleam under the sun. So how can a world presumably covered in ice be so profoundly, deeply dark? The answer lies not in the ice itself, but in what has been done to it over billions of years. The constant bombardment of cosmic rays and solar ultraviolet radiation, which paints the surface red with tholins, is also a powerful darkening agent. Those complex organic molecules are not just colorful, they are extremely efficient at absorbing light. Imagine taking a layer of pristine white frost and slowly, patiently, spraying it with a fine mist of crude oil or tar. Each microscopic droplet would coat the icy grains, trapping light rather than letting it bounce away. Over eons, this process can transform a bright icy landscape into a vast, lightless plain. The tholin coating acts like a cosmic soot, a permanent stain that has seeped into the very texture of the surface. But there is another, more physical possibility. The outer solar system is not a perfectly clean void. It is filled with microscopic dust, particles of carbon and silicates that are the ground-up remains of countless collisions and disintegrated comets. This dark dust slowly settles on the surfaces of distant worlds like a fine black snow. If Varuna's surface gravity is too weak to regularly refresh itself with clean ice from below, this cosmic dust could simply accumulate, creating a thick, dark blanket that smothers the inherent brightness of the ice beneath. The truth likely involves a grim partnership between both processes. Radiation cooks the surface ices into a dark organic sludge, and interstellar dust steadily rains down, mixing into a uniform, light-absorbing layer. This makes Varuna's surface a kind of cosmic attic, where the primordial ices of the solar system's birth have been left to gather an unimaginably ancient layer of grime. Its low albedo is therefore a direct measurement of its age and isolation. It tells us that Varuna's face has been exposed and chemically processed for the entire history of the solar system, with very little geologic activity to turn over a fresh, bright page. It is a world that has been sitting in the same dark room, collecting dust on its frozen furniture for 4.5 billion years. This darkness is not an absence, but a record, a somber testament to the relentless and transformative power of deep time in the silent reaches of space. This profound darkness is a product of its lonely journey, a path carved through space that holds its own cryptic story. The orbit of Varuna is not a simple, placid circle around the sun. It is an ellipse, a stretched-out loop that carries it from a point roughly 3 billion miles from the sun at its closest approach, all the way out to over 4 billion miles at its most distant. This path takes about 280 Earth years to complete, but the real intrigue lies not just in the shape of this orbit, but in its precise timing, its rhythm relative to the solar system's giant sentinel, Neptune. Astronomers meticulously track these distant dances, looking for patterns called orbital resonances. A resonance is a gravitational harmony, a stable, repeating ratio between the orbital periods of two bodies. For example, Pluto completes 2 orbits around the Sun for every 3 orbits of Neptune, a 2 to 3 resonance that protects Pluto from ever colliding with the giant planet, their paths locked in an eternal, synchronized avoidance. The question is, does Varuna sing in a similar, if fainter, harmony? Some detailed analyses of its motion suggest a tantalizing possibility, a weak gravitational link. The data hints that Varuna might be in a tenuous 3 to 4 resonance with Neptune. This would mean that for every 3 trips Varuna makes around the Sun, Neptune completes 4. It is not the strong, clear lock that Pluto enjoys, but more of a gentle, recurring nudge, a whisper of an ancient relationship. If confirmed, this faint resonance would be a seismic clue to Varuna's past. It would mean this dark, solitary world was not always so isolated. Billions of years ago, during the solar system's violent youth, the giant planets are believed to have migrated, shifting their positions in a grand gravitational reshuffling. As Neptune moved outward, its immense gravity would have swept through the primordial disk of icy debris, scattering most objects but capturing a fortunate few into these stable resonant orbits. For Varuna to be in even a weak resonance suggests it was once a participant in that chaotic era. It may have been gently herded, not ejected into the depths of interstellar space or flung inward, but placed delicately on its current path by the passing influence of the migrating giant. This transforms Varuna from a passive relic into an active witness. Its orbit becomes a frozen record of planetary migration, a trajectory calculated by the motions of planets in motion. The mystery deepens because the resonance is weak and debated, not a clear-cut fact. This uncertainty itself tells a story. Perhaps Varuna was only loosely captured, forever teetering on the edge of stability, a reminder that not all gravitational relationships in the early solar system were perfectly settled. Or maybe its orbit has been subtly perturbed over eons by the gentle, cumulative tugs of other large Kuiper Belt objects, slowly blurring the original resonant signature. Determining the truth requires tracking its position with exquisite precision over decades, a painstaking effort to decode the faintest echo of a gravitational event that occurred when the Earth itself was still forming. The riddle of its resonance is ultimately a question of origin, asking whether Varuna's lonely path is the result of a careful cosmic placement, or merely the aftermath of a gentle, forgotten scattering. The darkness of its surface holds a deeper secret, one that radiates in a spectrum we cannot see. Astronomers study distant worlds not just with visible light, but by listening to their faint, thermal whispers in the infrared. Every object in space, no matter how cold, emits a subtle glow of heat, a signature of its temperature and composition. Varuna is no exception, but when scientists point sensitive infrared telescopes toward it, the data returns a puzzle. The amount of heat it emits, its thermal infrared signature, does not neatly align with what the models predict for an object of its estimated size and presumed makeup. Think of it like holding your hand near what you believe is a simple block of ice. You expect a certain level of coldness radiating from it, a predictable chill. But with Varuna, the sensed temperature is off, either slightly warmer or cooler than anticipated. This thermal discrepancy is a quiet but significant alarm bell, signaling that our assumptions about this world are incomplete. One explanation could lie in the bizarre nature of its dark red surface. That thick coating of tholins and cosmic dust is not just visually dark, it is thermally complex. Such materials can have unusual thermal properties, perhaps acting as an inefficient insulator or a strangely effective radiator, altering how heat from the distant sun is absorbed, stored, and re-emitted back into space. A patchy, uneven surface, with some areas darker and some slightly brighter, would create a mottled thermal map, with hot spots and cold spots that confuse our average measurements. But there is a more radical possibility whispering from this thermal mismatch. The discrepancy could hint at a trickle of internal warmth. For a world so far from the sun, this seems almost heretical. Its surface temperature is barely above absolute zero, a cold so profound it defies human experience. The idea of internal heat typically belongs to active worlds like Jupiter's volcanic moon Io, or even Pluto, which is believed to have a subsurface ocean kept liquid by radioactive decay in its core. Could Varuna, a smaller and seemingly inert body, harbor any form of internal energy? If it does, the source would be faint but fascinating. The most likely candidate is the slow, persistent decay of radioactive elements locked within its rocky core, a tiny nuclear furnace that has been burning since its formation. Even a minuscule amount of this residual heat, trapped under an insulating blanket of ice, could create a subtle thermal gradient, making the world's emissions slightly different from a corpse that is cold all the way through. Another source could be tidal heating, but that requires a gravitational dance with a nearby partner, and Varuna has no known moons, unless, of course, its rapid, distorted spin itself generates a small amount of internal friction as its shape flexes under stress. These are fragile hypotheses, but the thermal data refuses to dismiss them entirely. This makes the mystery of its emission a profound detective story. The faint infrared glow we detect is a composite signal, a blend of reflected sunlight, surface temperature, and perhaps a whisper of something from deep within. Disentangling that signal is like trying to hear a single instrument in a symphony played from 4 billion miles away. Each new observation sharpens the picture, forcing us to ask if Varuna is simply a cold, dark rock with a strange coat, or if, against all odds, it still cradles a fading ember of its ancient formation heat, a secret warmth in the perpetual night. That faint thermal whisper and its distorted shape lead us to a startling possibility about its very structure. Could Varuna be not one world, but two? The theory suggests this distant, elongated body might be a contact binary, two separate objects that drifted together in the ancient past and now gently touch, forever frozen in a slow-motion embrace. We have seen this architecture before in the Kuiper Belt, most famously with Arrokoth, the snowman-shaped world visited by the New Horizons spacecraft. Arrokoth is clearly two distinct lobes joined at a narrow neck, a pristine fossil from the solar system's first building blocks. For Varuna, the evidence is more circumstantial, but compelling. Its extreme elongation, that stretched football shape we deduced from its light curve, fits the profile perfectly. If it were two spherical or ellipsoidal bodies pressed together, the combined form would naturally create an elongated silhouette. The rapid 6.34-hour rotation also supports this idea. A contact binary, with its mass distributed across two lobes, can often spin faster than a single, solid object of the same size without flying apart, as the two components can adjust slightly in their gravitational dance. So the question becomes, are we looking at a single, warped world or a cosmic duet? The implications of each answer are monumental. If Varuna is a single body, its elongation is a testament to the sheer force of its spin, a world permanently strained by its own momentum. But if it is a contact binary, it becomes something far more significant, a direct window into the gentlest processes of planetary birth. In the earliest days of the solar system, the disk of dust and ice was filled with countless small planetesimals. The prevailing theory for how they grew into larger bodies involves a slow, gentle process called cloud collapse. Instead of violent, high-speed collisions that would shatter fragile ice, these primordial chunks simply drifted together in the thin solar nebula, their relative speeds so slow that they could kiss and stick, merging through nothing more than their own weak gravity. A contact binary is the perfect end product of this process, a snapshot of that final, tender merger. Varuna, as a potential large-scale example, would be a king-sized Arrokoth, suggesting this gentle accretion was not just for small objects, but could build worlds hundreds of miles across. The evidence against the idea, however, is its very survival. Varuna spins incredibly fast, and such a rapid rotation could exert stress on the delicate neck joining two lobes, potentially threatening to pull the binary apart over time. Furthermore, its low density and presumed porous interior might argue for a more uniform, if fragile, rubble pile structure rather than two distinct components. Yet, perhaps its porous nature is the key to its cohesion, allowing the two lobes to settle and interlock like two piles of icy gravel gently poured together. For now, the truth remains just out of focus, a blur in the distant telescope's eye. Confirmation would require a direct image with resolution far beyond our current capabilities, a mission that may not happen for decades. So we are left with a profound and beautiful mystery, a question that strikes at the heart of creation itself. Is Varuna a solitary world stretched thin by its own fierce day? Or is it a fossilized embrace, two ancient souls that found each other in the dark and decided never to let go? The answer defines not just Varuna, but the very story of how our cosmic neighborhood was built, piece by gentle piece. Its potential double nature only makes the blankness of its face more unsettling. The spectrum of Varuna, the chemical barcode we read from its reflected sunlight, presents a profound and puzzling simplicity when astronomers break its faint light into a rainbow of wavelengths, searching for the dark lines that would betray the presence of specific molecules. They find an unsettling smoothness. Where we might expect to see the deep, clear absorption bands of water ice or the distinctive signatures of frozen methane, the spectrum is often muted, almost featureless. This is not what we anticipate from a world we believe is covered in ice and painted with complex organics. It is like listening for a symphony and hearing only a faint, uniform hum. One compelling explanation is that Varuna's surface is not a patchwork of different materials, but a globally uniform layer, that dark red Thalin sludge, created by billions of years of radiation, may have formed a thick, homogeneous blanket that completely masks the icy bedrock below. Think of it as a world covered in a single, unbroken sheet of dark plastic wrap. The light we see isn't reflecting off diverse ices, but bouncing off this one consistent, processed material, giving us a spectrum that speaks of the coating, not the world beneath. This would mean the relentless radiation has not just stained Varuna, but has fully cooked its entire surface into a single, monotonous substance, erasing all regional chemical diversity. Yet, there is another, more technological layer to this mystery. Our instruments are straining at their absolute limits. Varuna is a point of light so faint it tests the capabilities of our greatest telescopes on Earth and in space. The signal we receive is incredibly weak, and noise from our own atmosphere and instruments can easily smear out subtle spectral features. It is like trying to read the fine print on a sign from miles away through a thick, rippling heat haze. The faint absorption bands of water ice or methane might be there, but they are drowned in the murk of distance. Our current technology may simply be incapable of resolving the delicate chemical fingerprints we know must exist. This leaves us at a frustrating crossroads. Does the smooth spectrum reveal a truly bland, globally processed world, or does it merely highlight the limits of our own perception? Future observatories, like the next generation of giant ground-based telescopes or ambitious new space missions, will have the power to settle this. They could dissect Varuna's light with exquisite precision, perhaps revealing that its surface is a complex mosaic after all, with patches of relatively clean water ice hidden in shadowy craters, or streaks of different organic compounds painted by ancient cryovolcanic flows. For now, the featureless spectrum stands as a silent challenge, a reminder that some of the universe's most profound secrets are hidden not by darkness, but by a deceptively smooth and unreadable surface. This chemical blankness makes its position in the solar system's family tree all the more puzzling. To understand Varuna, we must see it not in isolation, but as one member of a vast, diverse population, the Kuiper Belt. This distant realm is not a uniform ring of identical ice balls, but a structured archive of the solar system's history, divided into distinct families based on their orbits and compositions. The most primordial group are the cold classical Kuiper Belt objects. These bodies orbit in nearly circular, flat paths close to the plane of the solar system. They are thought to be the true, undisturbed relics, having formed in place billions of years ago and never experiencing significant gravitational disruption. They are the solar system's original ice, preserved in the deep freeze. Then there are the hot population objects. These have more tilted, eccentric orbits, suggesting they were violently scattered by the gravitational migrations of the giant planets in the ancient past, their paths heated and stirred by those cosmic encounters. So, where does Varuna, with its elongated shape and frantic spin, belong? The answer is not clear-cut, and that is the core of the mystery. Varuna's orbit has a moderate inclination and a notable eccentricity, characteristics that would seem to place it squarely in the hot population, a scattered refugee from a more chaotic era. Yet, other aspects of its nature whisper a different story. Its dark red color, while not unique, and its apparent lack of surface ice diversity feel more aligned with some of the ancient, processed surfaces seen in the cold classical region. It is as if Varuna possesses a hybrid identity, bearing the orbital scars of a turbulent past while wearing the weathered face of an ancient resident. This makes it a profound outlier, a world that does not fit neatly into our established categories. The central question of its origin story hinges on this mismatch. Did Varuna form roughly where it is now, a local product that was later jostled into its current eccentric path by a close encounter with another large object, perhaps even a now departed sibling? Or is its story one of epic migration? Could it have formed much farther out, in the theoretical realm of the scattered disk, or even the inner Oort cloud, only to be gravitationally punted inward by Neptune during the planetary migration era, finally settling into its present uneasy orbit? Each origin story paints a different portrait of the world. A local formation suggests its fragile, porous structure might be typical for its original birthplace, a testament to the gentle accretion processes in that specific part of the primordial disk. An inward scattering from the frigid depths, however, implies it is a captured exile, a visitor from an even colder and more mysterious region, carrying with it the unique chemical and physical properties of a place we have never directly observed. Its current orbit is the only clue left from that ancient journey, a frozen trajectory that we must decode. Solving this mystery is not just about labeling Varuna, it is about mapping the gravitational currents of the early solar system. This solitary, dark world is a single piece of driftwood washed up on the shore of the observable Kuiper Belt, and we must trace the tides that brought it here. That smooth, featureless spectrum might hide a surface far more dynamic than we can see. The very idea of volcanoes on a world where temperatures approach absolute zero seems like a contradiction in terms. Yet across the outer solar system, we have found that cold does not mean dead. Cryovolcanism, the eruption of icy slush instead of molten rock, reshapes worlds from the nitrogen glaciers of Pluto to the tiger stripes of Enceladus. For Varuna, a body with such a rapid spin and potential internal warmth, the question is not just academic. Could this dark, elongated world have once been, or perhaps still be, a site of frozen geological fury? The driving force would not be the fiery magma of Earth, but a far gentler, colder engine. Residual heat from its formation, locked away for billions of years, or the slow, persistent decay of radioactive elements in a rocky core, could provide just enough energy to maintain a slushy, subsurface ocean of water mixed with antifreeze agents like ammonia. This briny liquid, under pressure, might occasionally seek a path to the surface. Imagine not a fiery explosion, but a slow, viscous ooze. A cryovolcanic eruption on Varuna would likely be a sluggish event. A thick slurry of water, ammonia, ice, and dark organic compounds welling up from below, spreading across the landscape like cold pancake batter before freezing solid in the relentless vacuum of space. Such an event would not build towering mountains, but could create smooth, plain-like regions or strange, dome-shaped features, patching over ancient craters and refreshing the surface with bright, clean ice. The evidence for this is faint and entirely circumstantial, but it exists in the puzzle of its color variations. Recall that Varuna's deep red hue is not perfectly uniform. Some areas appear slightly less red than others. One compelling explanation for these subtle differences is cryovolcanic resurfacing. A fresh eruption of relatively clean, ammonia-rich water ice from the interior would initially be bright and pale, a stark contrast to the surrounding dark Thallan plains. Over millennia, that new surface would itself be bombarded by radiation, slowly cooking into the same dark red goo, but for a time, it would stand out. These faint color patches could be the lingering scars of ancient eruptions, the last visible traces of geological activity that has long since fallen silent. The implications of even past cryovolcanism on Varuna would be revolutionary. It would mean that internal heat, and possibly subsurface oceans, are not the sole province of large moons or dwarf planets like Pluto. Even modestly sized, distant worlds could retain the warmth needed for geological life. This transforms our understanding of the Kuiper Belt from a graveyard of inert fossils into a potential archipelago of worlds with complex, layered interiors. A Varuna with a history of cryovolcanism is a world with a differentiated interior, a place where rock settled to the core and lighter ices rose to the mantle, creating the chemical and thermal gradients necessary for activity. It suggests a past where its interior was warm enough to flow and occasionally breach the surface, painting over the ancient impact scars with its own frozen breath. For now, these ideas remain in the realm of tantalizing speculation, constrained by a single point of light 4 billion miles away. Confirmation awaits a visitor, a spacecraft that could map its topography in detail, searching for the telltale domes, flows, and calderas of a world that once, against all odds, managed to whisper its geology into the void. The silent bombardment of space never ceases. While we ponder internal heat and ancient eruptions, Varuna's surface endures a constant, invisible rain. Every second, charged particles streaming from the sun as solar wind, and even more powerful cosmic rays from deep space, slam into its frozen crust at nearly the speed of light. This relentless assault is not a gentle weathering, but a transformative violence operating on an atomic scale. When a high-energy proton or cosmic ray strikes a simple molecule of methane or nitrogen ice on Varuna's surface, the impact is catastrophic for that tiny structure. It shatters chemical bonds, blasting apart the orderly arrangement of atoms. In the chaotic aftermath, these broken pieces recombine into new, far more complex molecules they would never form under normal conditions. This is the birth of Thallans, the dark red organic goo that paints Varuna crimson. Think of it as a billion-year-long chemistry experiment, where the radiation is the Bunsen burner and the primordial ice is the ingredient slowly cooking into an ever thicker, ever darker tar. But the mystery lies in the details we cannot see from here. What is the exact recipe? How long does it take for a pristine white patch of ice to turn a deep blood red? Is the process a slow, steady darkening, or does it happen in rapid jumps after periods of intense solar activity? Varuna, lacking a protective magnetic field or a thick atmosphere, is completely exposed to this cosmic irradiation. This makes it a perfect natural laboratory, a passive experiment that has been running since the solar system began. By studying the depth and uniformity of its dark coating, scientists can reverse engineer the history of radiation in the outer solar system. The variations in its redness act as a cosmic clock, with the deepest hues marking the oldest, most irradiated surfaces, and the lighter patches hinting at areas recently turned over, their chemical clocks reset. This relentless processing means the surface we see is not the original material of Varuna, but a radiation-made mask, a crust that has been chemically altered to its very core by the endless storm of particles from the Sun and the galaxy beyond. This cosmic chemistry experiment depends on a single, fundamental measurement we still struggle to pin down. The riddle of Varuna's true size and mass is not a minor technicality. It is the master key to unlocking everything else. To understand what this dark world is made of, we must first know how big it is and how much it weighs. And on both counts, our best estimates remain frustratingly uncertain. Different observation techniques tell subtly different stories, creating a debate that echoes across astronomical journals. One of the most reliable methods is to catch Varuna in the act of passing in front of a distant star, an event called an occultation. When this happens, the star's light winks out for a precise moment, and by timing that disappearance from multiple locations on Earth, astronomers can trace the exact outline of Varuna's shadow, measuring its diameter with remarkable accuracy. These rare occultation events have been captured, but they provide a snapshot of its shape from one specific angle. Given Varuna's extreme elongation, if we see it occult a star along its long axis, we get one measurement. If we see it from the side, we get another. The data suggests an average diameter somewhere around 420 to 450 miles, but the true three-dimensional shape complicates a single, simple number. The other major technique relies on its faint thermal glow. By measuring the infrared heat it emits and combining that with an estimate of its reflectivity, scientists can calculate how large an object must be to produce that specific amount of warmth. This thermal method, however, depends heavily on assumptions about the surface's properties. Is the dark thallen coating a perfect radiator, or does it trap heat strangely? Is the temperature uniform across its modeled surface? Small uncertainties in these assumptions lead to noticeable swings in the calculated size. The thermal estimates sometimes suggest a slightly larger or smaller world than the occultation data implies, leaving a margin of error that spans tens of miles. This might not sound like much, but on the scale of planetary science, it is a chasm. The problem compounds when we try to weigh Varuna. Without a moon to provide a clear gravitational tug, determining its mass is an exercise in indirect inference. Astronomers study the minute gravitational influence Varuna might have on the paths of other, even more distant objects, or analyze the orbits of hypothetical binary companions that have never been confirmed. The result is a mass estimate with wide error bars, and here lies the heart of the mystery. Density is mass divided by volume. If both the numerator and the denominator in that equation are uncertain, the resulting density, the single most telling clue about what Varuna is inside, becomes a blurry guess. A higher density would point toward a significant rocky core, giving the world structural strength to withstand its fierce spin. A lower density would argue for an even more porous, fragile rubble pile, perhaps with those vast internal cavities. A difference of just a few tenths of a gram per cubic centimeter shifts the entire internal model from a relatively solid world to a cosmic sponge. This uncertainty paralyzes our understanding of its history. Is Varuna a differentiated body, with rock settled at its heart and ice layered above, a structure that could support past cryovolcanism? Or is it a primordial, homogeneous lump of icy rubble, never warm enough to separate into layers? The answer is written in the density we cannot yet read with precision. Every other mystery, its rapid spin, its potential for internal heat, its strange shape hinges on this one unresolved number. We are trying to diagnose the health and history of a patient whose height and weight we can only estimate from a silhouette on a wall 4 billion miles away. Until a spacecraft visits or we are gifted with a perfect series of occultations, Varuna's true nature remains just out of reach, its essence hidden by the very shadows it casts. That blurred silhouette holds the frozen ingredients of creation itself. Varuna's profound distance and isolation are not merely obstacles to study, they are its greatest scientific gift. This world is a pristine relic, a time capsule from the solar system's violent birth over 4.5 billion years ago, preserved in the deep freeze of the Kuiper Belt. While planets like Earth and Mars have been utterly transformed by geology, weather, and life, their original building materials melted, mixed, and recycled beyond recognition, Varuna has remained in a state of suspended animation. Its surface, for all its dark radiation processing, still rests upon layers of material that have never been heated enough to melt or churned enough to homogenize. This makes it a direct sample of the protoplanetary disk, that swirling cloud of gas and dust from which every planet, moon, and asteroid eventually formed. The mystery is not whether it contains these primordial materials, but exactly which ones, and in what proportions. What was the precise recipe in this part of the nascent solar system? Was it rich in water ice, or did it also contain vast stores of frozen nitrogen, carbon monoxide, and methane? Were the dust grains intermixed with the ice the common silicates we see everywhere? Or did they include rarer, more volatile compounds that could only survive in this perpetual deep freeze? Varuna is a locked archive, and its composition is the original text of our solar system's first chapter. Decoding that text, however, is a monumental challenge. The very conditions that preserve it also hide it. That ubiquitous layer of dark tholins is like a veil over the archive's pages, a radiation-induced rewrite that obscures the original handwriting. Our telescopes, straining from across the solar system, can only analyze the surface of that veil. To read the pristine material beneath, we would need to look deeper, perhaps at fresh material exposed in a recent impact crater, or better yet, to physically sample it. Imagine if we could retrieve even a tiny grain of ice from Varuna's interior. That grain would be a microscopic window back to before the Earth existed. It could tell us the temperature and density of the protoplanetary disk in this region, hinting at how quickly planets could form. It could contain isotopic ratios, specific fingerprints of atomic varieties, that reveal which ancient stellar explosions seeded our solar system with its heavy elements. It might even hold presolar grains, tiny dust particles that formed around other stars long before our sun was born, the literal stardust from which everything here is made. These are the fundamental clues to our own cosmic origin story, and they are sitting, locked in ice, on a dark, spinning world 4 billion miles away. The tragedy is that for now, and likely for decades to come, this time capsule remains unopened. We can only infer its contents from the faint, distorted signals it sends back. Each new observation is an attempt to listen to the echo of creation, a whisper so faint it is almost lost in the silence of space. Varuna does not just orbit the sun, it orbits the very beginning of everything we know. That pristine time capsule might not be alone in its orbit. Circling Varuna, invisible to our most powerful telescopes, there could be a ghostly halo or a faint, ethereal disk. The search for rings or a debris disk around this distant world is a hunt for the faintest of whispers, a testament to how even the most subtle features can rewrite a world story. We have found rings in astonishing places, not just around the giant planets, but encircling small, icy bodies like the centaur Chariklo and the dwarf planet Haumea. Their presence reveals a history of violent disruption, a relatively recent collision that shattered a moon or a passing object, grinding it into a cloud of particles that gradually settled into a flat, orbiting band. For Varuna, the possibility is tantalizing. Its rapid, distorted spin and lonely state are exactly the kind of clues that might point to a cataclysmic impact in its past. Such a collision could have generated a temporary cloud of debris, some of which might have coalesced into a moon, while the rest spread out into a ring. The gravitational forces at play, however, are incredibly weak. Varuna's gravity is a faint whisper, and maintaining a stable ring in such an environment is a delicate balancing act. Stray particles would be easily lost to the solar wind or tugged away by the subtle gravity of the Sun and Neptune. Any ring system would likely be transient, perhaps only lasting for a few thousand or million years before dissipating into space. This means if we found one, it would be a sign of a remarkably recent event, a geological yesterday on the scale of the solar system. So how do you search for something so faint and distant? Astronomers do not look for the rings directly, as they would be far too dim to see. Instead, they wait for another cosmic alignment, an occultation. When Varuna passes in front of a distant star, they meticulously monitor the starlight. If the world has rings, the star's light would not simply wink out and then reappear. In the moments before and after the main occultation, there would be additional, brief flickers or dips in brightness as the star's light passes through the tenuous ring material. It is like watching someone walk behind a picket fence. You see them disappear not all at once, but in a series of glimpses between the slats. These events require impeccable timing, a network of observers across the globe, and a tremendous amount of luck. So far, no confirmed ring signatures have been detected around Varuna, but the absence of evidence is not evidence of absence. We may simply have not caught it in the right orientation, or our observations have not been sensitive enough. The implications of a discovery, however, would be profound. A ring would be a smoking gun for a recent, violent impact, directly explaining its rapid spin and potentially its lack of moons. It would mean Varuna is not a quiet relic, but an active participant in the ongoing, slow-motion demolition derby of the Kuiper Belt. Even more intriguing than a narrow ring is the possibility of a broader, diffuse disk of dust. This would be the longer-lasting aftermath of a collision, a cloud of fine powder slowly spiraling inward or drifting outward. Such a disk would be even harder to detect, but its thermal signature might add another layer of confusion to Varuna's already puzzling infrared emission, a faint, extended glow that our telescopes perceive as part of the world itself. The hunt for these spectral features continues, a patient vigil for a flicker within a flicker, a hint that this solitary sentinel's past was far more dramatic than its dark, silent present suggests. The absence of rings does not mean Varuna's environment is static. Its bizarre shape and orientation create a hidden, slow-motion drama of climate. Every world with a tilted axis experiences seasons, a rhythmic change in how sunlight strikes its surface. Earth's 23-degree tilt gives us summer and winter. Varuna's axis is also tilted, but its profound elongation adds a confounding layer of complexity. This is not a simple sphere rotating under a steady sun. Instead, it is a stretched, lopsided top, spinning furiously, with one hemisphere potentially receiving vastly different amounts of solar energy than the other, not just because of tilt, but because of its very form. The result is a seasonal cycle of almost unimaginable subtlety and strangeness. Imagine a potato slowly twirling in a dimly lit room. As it turns, some of its bulging, rounded sides will face the light source more directly, while its pointed ends may only catch a glancing ray. Now, make that potato hundreds of miles wide, coat it in volatile ices, and place it 4 billion miles from a light bulb. That is the essence of Varuna's climate. Solar heating is not uniform. It becomes a patchwork, intensely dependent on local geometry. A broad, flat face presented to the sun during its closest orbital approach might warm up a fraction of a degree more than a narrow ridge pointed at the sun during its distant orbital retreat. This tiny thermal variation in the extreme cold of the Kuiper Belt could be the difference between a frozen state and a sublimating one. On a world where temperatures are only a few tens of degrees above absolute zero, a single degree can unlock a volatile. A patch of nitrogen ice on a sun-facing bulge might gain just enough energy for its molecules to break free, turning directly from solid into a wisp of gas. That gas, however, has nowhere to go. Varuna's gravity is too weak to hold a substantial atmosphere, so these liberated molecules do not linger to create clouds or winds. Instead, they perform a slow, silent dance across the surface. Drifting in the near vacuum, they will eventually encounter a colder region, perhaps a permanently shadowed crater on the world's narrow end, or an area tilted away from the sun. There, they will lose their minuscule energy and freeze back onto the surface as a fresh layer of frost. This creates a form of precipitation, a transfer of material from the warm areas to the cold ones, painting the surface in a constantly shifting, billion-year-long watercolor of frost and dark thalin. The seasons themselves are drawn out over centuries. A Varuna year lasts 280 Earth years. A single season, from its version of summer solstice to winter solstice, could span 70 Earth years or more. This means the climate patterns we are theorizing about operate on timescales longer than human civilization. A region might be a zone of net sublimation, actively losing its volatile ices for decades, only to slowly become a zone of net deposition, a cold trap collecting frost for the next several decades. The surface we see in any given astronomical observation is just a single frame in an epic, slow-motion film. The variations in its red coloration could be the lingering scars of these ancient seasonal migrations, with darker areas representing ancient bedrock of thalins where volatiles have long since boiled away, and slightly brighter patches marking cold traps where fresher frost has recently accumulated. This idea transforms Varuna from a static fossil into a world with a dynamic, if incredibly sluggish, metabolism. It breathes, not with an atmosphere, but with a slow exchange of frost across its tortured geography. Its climate is a silent ballet of ice and shadow, choreographed by its misshapen form and the faint, distant rhythm of a dying star. This profound solitude might be an illusion of our limited perspective. While Varuna itself lacks a moon, its loneliness could extend far beyond a single missing satellite, into the very fabric of its celestial neighborhood. Astronomers have begun to ask a deeper question. Is Varuna truly a solitary wanderer, or is it the largest surviving member of a hidden family, a cosmic clan scattered across the Kuiper Belt? This idea moves the mystery from a single world to a ghostly constellation. The theory proposes that Varuna, along with several other specific Kuiper Belt objects we have cataloged, might all be fragments from a much larger, primordial body that suffered a catastrophic breakup billions of years ago. This would not be a gentle separation, but a shattering impact of unimaginable force, a collision that blasted an ancient world into pieces, sending its children spiraling out on similar, but not identical, paths around the sun. The evidence for such a family would not be written in proximity, as these fragments would now be millions of miles apart, but in the subtle mathematics of their orbits. Scientists perform intricate statistical analyses on the orbital elements of thousands of known Kuiper Belt objects, their tilts, their eccentricities, the shapes and orientations of their paths. They search for clusters, groups of objects whose orbits share a common mathematical fingerprint, suggesting they all originated from the same point in space and time. Finding Varuna within such a cluster would be a revelation. It would mean this dark, elongated world is not an orphan, but a survivor, the biggest piece of a shattered progenitor. Its rapid spin and strange shape would suddenly make perfect sense as the legacy of that ancient violent shattering. The other objects in this hypothetical family would be its siblings, smaller shards of that same primordial body, each carrying a piece of the original's composition and history. This transforms our understanding of its origin from a gentle accretion story to one of cosmic demolition and rebirth. The search for this family is like detective work on a galactic scale, sifting through the random drift of countless ice chunks to find the ones that move with a shared, inherited rhythm. It is a painstaking process, as gravitational nudges from planets and other objects over billions of years have slowly dispersed and altered the orbits of any original cluster, blurring the familial signature. A confirmed dynamical family for Varuna would be a direct window into one of the most violent and common processes in the early solar system, the collisional fragmentation that shaped the population of the Kuiper Belt. It would tell us that even the larger denizens of this realm were not immune to being broken apart, and that what we see today as individual worlds might often be the reassembled rubble of even grander, lost ancestors. For now, no definitive family has been conclusively linked to Varuna, leaving it in a tantalizing limbo. It may be the patriarch of a dispersed dynasty we have yet to fully recognize, or it may remain a true singleton, a world whose formation story is uniquely its own. The answer lies in the silent mathematics of motion, waiting to be decoded from the slow dance of 100 distant points of light. Its lonely path and hidden family lead to a question of cosmic identity. Is Varuna a dwarf planet? This is not a simple label, but a profound debate that strikes at the very definition of what makes a world a world. The official criteria set by the International Astronomical Union are deceptively simple. To be a dwarf planet, an object must orbit the sun, not be a moon, and crucially, have sufficient mass for its own gravity to pull it into a nearly round shape, a state called hydrostatic equilibrium. It is this final requirement that places Varuna in a shadowy zone of classification. On one hand, its estimated size and mass suggest it should have enough gravity to achieve that round shape. Many objects smaller than Varuna, like Saturn's moon Mimas, are spherical because their material is strong enough, and their gravity sufficient to overcome the rigidity of rock and ice. By the numbers, Varuna should qualify, yet our observations tell a conflicting story. The meticulous analysis of its light curve reveals not a sphere, but that profoundly elongated, football-like shape, stretched thin by its furious rotation. This presents a direct contradiction. If it is in hydrostatic equilibrium, why is it not round? The answer may lie in the delicate balance between force and form. Hydrostatic equilibrium is not a binary state of round or not round, but a spectrum. It describes a body where gravity is the dominant force shaping it, pulling material evenly toward the center. But other forces can compete. For Varuna, its extreme rotational speed generates a powerful centrifugal force that pushes material outward at its equator, actively working against gravity's pull to create a sphere. It is a cosmic tug-of-war, and for Varuna, spin is winning. This means it may indeed be in a kind of equilibrium, but a distorted one, a rotational equilibrium where its elongated shape is the stable compromise between gravity pulling in and spin pulling out. So, does it meet the criteria? Purists argue no, because the definition implies a near-spherical shape, the classic form we see in Ceres, Pluto, and Eris. Pragmatists counter that the physics is what matters, and Varuna's shape is the direct result of gravity balancing another fundamental force, a valid solution to the equilibrium equation. This classification limbo makes Varuna a critical test case. It exposes the fuzzy, often contentious line we draw in the cosmos. Our categories are human inventions, attempts to impose order on a natural world full of exceptions and continua. Varuna stubbornly sits on that boundary, challenging us to refine our definitions or accept the beautiful messiness of nature. Its disputed status tells us more about our own need for categorization than it does about the world itself. Is it a dwarf planet or a very large, very fast Kuiper Belt object? The answer may ultimately be less important than the question, for in wrestling with it, we are forced to confront the true, wondrous diversity of solar system bodies, a diversity that refuses to be neatly boxed. Varuna does not care about its label. It simply spins in the dark, a permanent question mark written in ice and shadow. That dark red stain is more than a simple coat of cosmic paint. It is a chemical laboratory, silently running experiments that have lasted for billions of years. The tholins that give Varuna its crimson hue are not just one substance, but a vast, messy family of complex organic molecules. They form when simple ices like methane are shattered by radiation, and their broken pieces recombine into new, larger, and more intricate structures. These molecules are rich in carbon, the fundamental building block of life as we know it. On Varuna, this process is happening in the most hostile environment imaginable, in near total darkness, and at temperatures colder than any place on Earth. This raises a staggering possibility. Could the frozen, airless wastes of the Kuiper Belt be unintentionally cooking up the raw ingredients for life? The idea seems to defy logic. We typically associate the chemistry of life with warm, watery environments, like the deep sea vents of Earth or the subsurface oceans of moons like Europa. Varuna offers neither warmth nor liquid. Yet its surface is a vast, passive reactor where cosmic radiation provides the energy, and primordial ices provide the feedstock. The thalins produced are what scientists call prebiotic molecules. They are not alive, not even close, but they represent the chaotic first steps down the long and improbable road toward biology. They are the kind of complex organic goo that, under the right conditions over immense stretches of time, could eventually lead to amino acids, the components of proteins and nucleobases, the letters of the genetic code. We have seen evidence of similar chemistry elsewhere. The famous Miller-Urey experiment in the 1950s showed that simulating the conditions of early Earth with electrical sparks could produce amino acids from simple chemicals. Varuna's surface is a natural, cosmic-scale version of that experiment, with radiation standing in for lightning. The Cassini spacecraft found thalins in the atmosphere and on the surface of Saturn's moon Titan, creating a thick orange haze and dark dunes. But Titan is relatively warm and has a thick atmosphere. Varuna is doing this in the absolute void, with no atmospheric pressure to speak of. This makes its ongoing chemistry even more remarkable. It suggests that the universe's drive toward complexity is relentless, operating even in the most frozen and isolated backwaters. The mystery is not whether these organics exist. We are virtually certain they do. The deeper question is what their specific recipe tells us. Are Varuna's thalins particularly complex? Do they contain molecular structures that are surprising for such a cold environment? Each variation in its red color could correspond to a different age or type of this organic sludge, a layered history of chemical experimentation. Finding out would require a spacecraft to fly through its faint exhalations or land on its surface and taste the dust. Until then, Varuna stands as a profound testament to a simple, awe-inspiring truth. The universe is not just a collection of rocks and ice. It is a chemist. Even in the perpetual night, 4 billion miles from the sun, it is quietly, patiently stirring the pot, mixing the primordial soup from which, somewhere else under kinder stars, something wondrous might one day emerge. All this speculation, from its internal warmth to its prebiotic chemistry, ultimately circles back to a single, humbling truth. We have reached the absolute limits of remote observation. Every mystery we have explored, every question we have asked about Varuna, is constrained by the same fundamental barrier, a distance of over 4 billion miles. From here, it is a single, faint pixel of light. We can analyze its flicker, dissect its color, and model its orbit, but we cannot see its surface, feel its gravity, or taste its ices. The definitive answers, the ones that would transform our understanding of this dark world and the early solar system, are locked away, accessible only by making the journey ourselves. This realization brings us to the final, practical frontier, the dream and the daunting challenge of a mission to Varuna. Sending a spacecraft to this distant outpost is not merely difficult, it is one of the most ambitious endeavors we could conceive in planetary exploration. The sheer distance is the first colossal hurdle. Even traveling at the incredible speeds achieved by the New Horizons probe, which flew past Pluto at over 30,000 miles per hour, a journey to Varuna would take decades. We are talking about a flight time of 30, 40, or even 50 years. This presents staggering engineering and philosophical challenges. A spacecraft must be designed to survive the brutal environment of deep space for half a century, its systems and instruments remaining functional after a journey longer than the careers of the scientists who built it. It requires power sources that can last for generations, communication systems that can whisper a signal back to Earth across a gulf, so vast that a single radio command would take over 6 hours just to arrive. And it demands a societal commitment, a promise from one generation to fund and follow a mission whose results will be delivered to the next. Yet, the scientific payoff would be nothing short of revolutionary. Imagine a hypothetical flyby, a fleeting encounter after a half-century voyage. As the probe approaches, its cameras would finally resolve that single pixel into a world. The first revelation would be its true shape. Is it a smooth ellipsoid stretched by spin, or a ragged contact binary, two lobes in a frozen hug? That single image would settle centuries of debate in an instant. As the spacecraft whizzes past, precise tracking of its trajectory would allow scientists to measure Varuna's gravitational pull with exquisite accuracy. For the first time, we would know its true mass. Combined with the exact volume determined from its shape, we would finally, definitively, calculate its density. That one number would unlock the interior. Does it point to a solid core or a porous rubble pile? Is there room for those vast internal cavities? Next, a suite of spectrometers would perform an intimate chemical analysis. They would map the surface, distinguishing between the dark red thallen plains and any patches of fresher, brighter ice, directly confirming or refuting theories of cryovolcanic resurfacing or seasonal frost migration. They could sniff the tenuous space around it, hunting for the molecules of a transient atmosphere, catching Varuna in the act of breathing. They could even analyze the dust environment, searching for the faint signature of a ring or debris disk, the ghost of an ancient collision. Each instrument reading would be a key turning in a lock, opening a door to a past we have only guessed at. Such a mission would not just solve the mysteries of Varuna, it would provide a pristine benchmark. It would show us, in perfect detail, what one of the solar system's original building blocks truly looks like, giving context to every other object in the Kuiper Belt and beyond. The data would flow back to Earth, a precious stream of bits traveling at the speed of light. And on some day decades from now, a new generation of scientists would open a file and see, for the very first time, the face of a dark god. Until then, Varuna remains a masterpiece of shadows, its secrets kept safe by the vast and silent ocean of space itself. The silent, frozen stability of its orbit is a temporary illusion. For all its ancient stillness, Varuna's path through the dark is not a permanent fixture of the solar system, but a single frame in a film that will play out over billions of years. Its ultimate fate is written not in its ice, but in the invisible web of gravity that connects it to everything else. The primary architect of its future is Neptune, the giant blue sentinel whose gravitational reach sculpted the Kuiper Belt in the past and continues to police it today. While Varuna may be in a weak, tenuous resonance with Neptune, that relationship is not a guarantee of eternal safety. Over immense timescales, the cumulative effect of countless gentle tugs can add up, like the steady dripping of water eventually wearing down stone. The gravitational influence of the other giant planets, Jupiter, Saturn, and Uranus, though much fainter at this distance, also contributes to a slow, chaotic dance. This creates a fundamental uncertainty in predicting where Varuna will be in 1,000,000 years, let alone 1,000,000,000. It exists in a state of dynamical fragility, its path perpetually susceptible to subtle alteration. Computer models that simulate the gravitational interactions of the outer solar system over eons reveal a spectrum of possible destinies for objects like Varuna, and none of them involve remaining perfectly, peacefully in place forever. One of the most likely long-term futures for Varuna is a promotion of sorts, a journey from the relative quiet of the Kuiper Belt into the chaotic inner realm of the giant planets. If a series of gravitational nudges from Neptune adds just the right amount of energy to its orbit, Varuna could be scattered inward. It would then become what astronomers call a centaur, an icy body with an unstable orbit that crosses the paths of the giant planets. We know many centaurs today, like Chiron and Chariklo, and they are thought to be recent refugees from the Kuiper Belt. This transition would mark a dramatic new chapter in Varuna's existence. No longer a distant, frozen relic, it would become an active participant in the violent gravitational arena closer to the Sun. As a centaur, its fate would be sealed within a much shorter time frame, perhaps only a few million years. The repeated close encounters with Jupiter, Saturn, Uranus, and Neptune would violently perturb its path. It could be flung back out to the Kuiper Belt or the Oort cloud, ejected from the solar system entirely to wander the galaxy as a rogue planetesimal, or set on a collision course with one of the planets or the Sun itself. The centaur phase is a cosmic purgatory, a temporary and tumultuous state from which few objects emerge unchanged. The most spectacular and final possibility, however, is a fiery transformation. If gravitational interactions send Varuna on a path plunging directly toward the inner solar system, it would undergo a radical metamorphosis. As it approaches the Sun, the increasing warmth would begin to activate its frozen volatiles. That dark, red thalline coating would crack and sublimate. The primordial ices locked within its porous interior would violently turn to gas, erupting from its surface in brilliant jets. Varuna would cease to be a dark, silent world and would blossom into a comet. Its long, lonely journey in the dark would culminate in a brief, blazing performance. For a short period, perhaps only centuries or millennia, it would grow a magnificent, glowing coma and a spectacular tail that could stretch across the sky, a temporary monument to its own destruction. This cometary phase would be its last act. Each close pass by the Sun would strip away more of its material. It could disintegrate completely, like Comet Shoemaker Levy 9, or break into a cloud of debris that slowly disperses along its orbit, leaving only a faint trail of dust. In this scenario, Varuna's ultimate fate is to become its own memorial, a shower of meteors that might one day streak through the atmosphere of a world like Earth, delivering fragments of its ancient, irradiated surface as a final gift. These models, while informed by physics, are ultimately probabilities, not prophecies. The solar system is a chaotic system, where the precise prediction of an object's path over billions of years is impossible. A single, unforeseen close encounter with another large Kuiper Belt object, though statistically rare, could alter its trajectory in ways our simulations cannot foresee. Varuna might, against the odds, remain in a stable enough orbit for the remaining lifetime of the Sun. It could be a witness to the Sun's expansion into a red giant 5 billion years from now, feeling a warmth it has not known since its formation before being engulfed or cast adrift. Its destiny is a tapestry of chance, woven by gravity over timescales that dwarf human history. This contemplation of its end brings a poignant weight to its current mysteries. Every measurement we take, every theory we craft about its shape and composition, is an attempt to understand a world that is, on a cosmic clock, already transient. We are studying a snowflake in a silent storm, trying to decipher its intricate structure before the wind changes and carries it away forever, into a future of fire or endless night. Yet, the most profound mystery of Varuna is not written in its ice or its spin, but in what its very existence means for us. This distant, dark, and distorted world, for all its scientific puzzles, presents a final philosophical enigma. What does Varuna truly represent? It is not a planet. It is not a classic comet. It exists in a categorical limbo, a solitary sentinel in a realm of perpetual twilight. In its stubborn refusal to fit our neat classifications, Varuna becomes a powerful symbol. It represents the vast, silent majority of our solar system, the countless unknown worlds that drift unseen in the dark beyond Neptune. For every Pluto or Eris we have found and named, there are likely hundreds, perhaps thousands of Varunas, each with its own unique shape, its own strange spin, its own hidden history. Our solar system is not merely 8 or 9 planets with a few interesting moons and a belt of asteroids. It is a sprawling, three-dimensional archipelago of icy worlds, a cosmic frontier far richer and more diverse than we ever imagined just a few decades ago. Varuna is our first clear message from that frontier, a whisper that tells us how little we truly know about our own celestial neighborhood. Its persistent mysteries, from its density to its internal heat, are not just scientific problems to be solved. They are humbling reminders. They underscore the limitations of our perspective, tethered as we are to our warm, rocky world so close to the sun. We project our expectations on the cosmos, assuming that what is true here must be true out there. We expect large bodies to be round, spin to be slow, and darkness to mean emptiness. Varuna defies every one of those expectations. It challenges our anthropocentric view, forcing us to expand our understanding of what a world can be. In doing so, it becomes a mirror for human curiosity itself. Why do we care about a faint speck of light 4 billion miles away? Because its very obscurity is a siren call. Each unanswered question about Varuna is a door cracked open, an invitation to venture further. This drive to explore, to categorize, and to understand the most distant and dim objects speaks to something fundamental in our nature. We are a species compelled to map the darkness, to find patterns in the chaos, to seek companionship in the cosmos, even if that companionship is a frozen, misshapen world that will never know we exist. Varuna, in all its silent mystery, ultimately represents the beautiful, endless dialogue between the human mind and the universe. We send our questions out into the void on beams of light and radio waves. And sometimes, if we are patient and clever, the void sends back an answer in the form of a flickering point of light that holds a universe of secrets. The story of Varuna is, therefore, not just the story of an ancient piece of ice. It is the story of our own longing to connect, to learn, and to find our place in a cosmos whose scale and complexity will always outpace our comprehension. It reminds us that the greatest discoveries often lie not in finding answers, but in learning how to ask better questions of the dark. Varuna's journey through our understanding has been a cascade of riddles. From its frantic 6-hour spin to its elongated, football-like shape, from a density so low it might float to a surface stained deep crimson by billion-year-old radiation, every answer only reveals deeper questions. We have probed the silence where moons should be, listened for the whisper of a transient atmosphere, and debated whether its smooth spectrum hides a bland world or simply our own technological limits. We have traced its potentially resonant orbit, felt for the phantom warmth of internal heat, and wondered if its fragile form is a single strained body or a fossilized embrace of two. Its profound darkness, its disputed status as a dwarf planet, its role as a primordial time capsule, and even the possibility of hidden rings or a scattered family. Each layer adds to a portrait of profound complexity. This is not a simple snowball at the edge of everything. It is a keystone. Unlocking Varuna's secrets would rewrite the story of our solar system's infancy, revealing the gentle or violent processes that built the frozen worlds beyond Neptune. It reminds us that the cosmos specializes in the exception, not the rule, crafting wonders that defy our every expectation. So the next time you look up at the night sky, remember that in the vast darkness beyond what you can see, a dark, misshapen world is spinning its mysteries in silence. It asks us to stay curious, to keep questioning, and to never assume the universe has shown us all its cards. Which of Varuna's 25 mysteries captures your imagination the most? Let us know in the comments below.